Alright guys, so today we're going to talk about tangent and normal vectors with the aim of talking about curvature. So today's going to be quite a theoretical video, but it should give you a lot of intuition as to what's going on. So firstly, let's recall that if we had a curve, I'm going to draw it without any axis, just a curve. We were able to find the tangent line in the previous video by taking derivatives, and this is, by the way, going to be given by a vector valued function, not prime but an arrow. So a vector valued function r is going to give us our curve, and then we're going to have a tangent line. But whenever we're doing this, we computed the tangent vector, and what we did is we just did r prime of t. But that vector right there, that followed, by the way, the direction of our curve. So we talked about all this before, so I'm just reminding you of what we talked about in the previous video. So we had a curve, we had a tangent vector, and what we're going to do now is we're going to say, well, we would want this vector to be a unit vector so we can actually do some calculations with it. So we're going to define that vector to be the principal tangent vector, and it's going to be called t of t. And in the book they would do it with bold because, well, they have bold, we don't, so we're going to keep doing our arrows. So it's going to be the vector r prime. By the way, I forgot my arrow here as I'm talking. So if you ever see one without an arrow, just put it there in your head. R is always going to be a vector for us right now. So I'm going to do r prime divided by its length. So just converting this vector into a unit vector. So that's going to be our principal tangent vector. So let's write it out. But now there is another vector that is rather interesting, and it's going to be the normal vector. So it's going to go in the perpendicular direction to our vector r, and that vector is going to be normal, and we're going to define it in this way. So the normal vector, which is perpendicular to the tangent vector t, I mean the direction there doesn't matter, is going to be defined by the same idea, t prime over the length. So now you will ask, how do we even know that that is perpendicular? Because we're not defining it in terms of any angle. And I'm going to go ahead and show you that in 1 second. In fact, it's rather straightforward. We're going to do it here so I can keep my objects that I'm defining there. And this is going to be kind of my workspace, if you will. So if you think about what t is, t is going to be a unit vector. So t, so this calculation really doesn't depend on t itself. It's just in the fact that it is a unit vector, so the length is 1. So when I divide by its length, I make it to be that, to be 1. And then that means that t dot t is equal to 1. But when I do then a product rule here, I take a derivative. Remember, for dot product, there is a product rule. So I get t prime dot t plus t dot t prime. So derivative of the first times the second plus the first time derivative of the second. Same idea. Derivative of 1 is a constant, so you get 0. Now, remember that the dot product is commutative in any real vector space, but in this case, we're talking about R2 or R3. So this is going to tell you that 2 times t prime dot t is equal to 0, from where you get that t prime, which is this one, is going to be perpendicular to or orthogonal to t, which was this one. Now, if this vector is perpendicular to this whole vector back here, it doesn't matter if you normalize it, if you make it a smaller or longer length, that's still going to be perpendicular. So that then tells you that this vector here is the, that's going to be normal. It's going to be the normal vector, principal normal vector, and is perpendicular to the principal tangent vector, or to any tangent vector for that matter. So those are the two we had. So we proved already that they are orthogonal to one another. So I'm going to talk briefly about the arc length for the curve. I'm going to remind you how to do it. We did it for parametric equations. It's the exact same thing. I just need to write a little bit of a tweak on the equation so we can use that for a calculation of curvature. All right, so let me erase here. I'll be right back. All right, so let's go ahead and look at recall the formula for the arc length, let's call it S, for a curve that is in parametric form. Let's do x, y, z for right now. And let's write it as the integral from a to b of the square root of the derivative of x prime of t. Actually, you know what? I'm going to do it just for 2 dimensions because of space. You would have a plus z squared here, dt. So if you have it like that, now it doesn't matter whether it's 2 or 3 dimensions, because the way I'm going to write it is going to be just the length of the vector r prime. So convince yourself that this is true. If you think about the magnitude of a vector is the square root of sum of the squares, and the entries of r prime we determined last time, or we talked about last time, the coordinates of r prime, that would have probably been a good idea to write for those who didn't watch the video before, are just going to be x prime and then y prime, and if you have z prime as well. Now I'm mixing 2 and 3 dimensions here, but this one, if it's 2 dimensions, this one is not here, and if this one is 3 dimensions, you just add the plus z prime squared. All right. In any case, this is the formula that I wanted to talk about, because then if you want to look at the differential of s with respect to time, then by using the first fundamental theorem of calculus, well, you would have to evaluate, wherever you're going to evaluate this, you'd have to evaluate the integral from a to a certain value of t, and then you would evaluate this with respect to another variable, let's call it v, if you will. And then when you take your derivative, then you know that you get just the integrand. So what that tells us is that the ds dt, or the rate of change of the arc length with respect to time, is nothing but the derivative, or the magnitude of the derivative of the function itself. All right, so that's going to be useful. At the moment, it probably doesn't tell us a whole lot, but in the next board, it will all make sense. So I'm going to go ahead and write it here, and I'm going to give you now, then we're going to start talking about curvature at this point. All right, so I'll copy, and I'll erase, and then I'll be right back. All right, so now we're at the point that we can start talking about curvature, and that's the objective, or why we introduce the tangent and normal vectors, because that's going to be important for us. The normal vector, not so much. What we care about is that t prime and t are going to be orthogonal, but we need it for our proofs. So let's go ahead and take a look at a curve. Let's assume you're driving around a mountain pass, and I made them pretty much the same curvature. Let me do one a little bit more of a curve. Let's say this curve is going to be rather tight. You're going to have a quick turnaround with respect to the other. We don't ever define, when we're driving, the concept of a curvature, but we feel it when we're driving. And if you were to be able to put a tangent circle around here, you'd have that this circle here is much smaller than what you can put in that one. And so we want to have an idea how to define the curvature. And so to do that, I'm going to go ahead and look at the tangent vector at 2 points, and I'm going to try to go just at the point of interest, let's say there, and I'm going to move just a little bit to the right on my curve. So the tangent will be somewhere around here. And now I'm going to go here, and I'm going to move more or less the same distance along the curve. I'm not doing anything about x, y, z, whatever. I'm just going around the curve. Why? Because when I go to 3 dimensions, well, usually we used to do ds dt or dx or whatever. Right now we don't know what to go over because I don't even have coordinates. So I'm just going to go ahead and move a little to the right by the same amount on my curve. Okay? And by the way, this looks almost like I have glasses or something. Anyways, I'm going to move just a little to the right, so about the same, and I'm going to look at the tangent vectors at both. So this is more or less there, and this one is more or less here. Now, notice that these two, they're not parallel by any stretch of the imagination, but this one is almost they're very close to each other, if you will, versus this one. This one's almost horizontal. This is very much going very slant upward. So you see the tangent vector here changed rapidly when the curve was very curvy, and here the tangent vector didn't change a whole lot when the curve was not as curvy. So what I'm going to define the curvature to be, or what is defined to be, is going to be named kappa, the Greek letter kappa, and it's going to be the magnitude of how much is the tangent vector, the normal tangent vector. And why do you want the normal? Well, because that will standardize how big your tangent vector is. So you want to compare unit tangent vector so that you kind of have an idea how it really is changing relating to the curve. So with respect to the change of the tangent with respect to the length of the curve. So that allows us to define the curvature independent whether we're doing it in 2 dimensions, 3 dimensions, or whatever. Because if we were going to do it in 2 dimensions, we would likely say, well, it's going to be dt over dx. We would like to do that. But now you move to 3 dimensions, and what do you make it be with respect to x, y? What do you make it to be? So it's best to just do it with respect to the length of the curve. And that's going to tell you how the tangent vector is changing just while you walk over the curve. And that then is very nice definition, because firstly it's kind of coordinate based, because it doesn't matter whether I'm in 2 dimensions or whatever. But makes it hard to compute because you have dt with respect to ds, and remember ds I said was that square root of x prime squared, and that's not a nice thing to do. So the first thing we need to figure out is a better formula for this. So to do that, I'm going to go ahead and compute dt by dt. So the rate of change of the normal, the principal tangent vector with respect to the time t. And I will use the chain rule to write this as dt ds, which is the quantity of interest, times ds dt. And then I say, well, lucky for me, this ds dt is nothing but what I wrote here on the other board, which is just the magnitude of r prime of t. Okay? Now, when I take magnitudes here, this right here is a scalar. So I can pull that out, and I can take magnitudes on this too. This right here is going to be a vector. This right here is going to be a vector. Take magnitudes, but this right here is a scalar. Can pull out. So I can get that the magnitude of dt by dt is going to be equal to the magnitude of dt by ds, which is also known as the curvature. That's how we defined it. And then the magnitude of r prime of t. So now I can solve, and I can get one formula for this curvature. This right here I'm going to replace with kappa. And I can divide both sides by this. This one is also known as t prime. So I can write my equation right here as the magnitude of t prime of t, which is divided by the magnitude of r prime. So this is already way more functional or more useful than what I had here as my definition. Because if I have a curve, r, that is given with respect to time, I can go ahead and take my derivative. I get that bottom part done. Then once I have the derivative, I divide by its length. I get t. Of course, this is going to be a ratio. This is going to be a quotient. So I'm going to have to do a quotient rule to take t prime. And regardless, I do t prime, take the magnitude, and I get that value. So I can already compute curvatures with this formula. This one, you do you. This one is already usable. But there's one that is perhaps a little bit easier to use, and it involves the cross product. So let's go ahead and try to write that one out. So maybe I'm going to make a list of all the formulas that we have here, and I'm going to use this still as my workspace. So I'm going to erase, write the formulas we have, and then I'll continue to compute others in the when I come back. All right, so I'll be right back.